Hiya folks, in this video we're going to try and summarise as much of the topic of fields, that's gravitational and electric fields, at A2. We're going to try and summarise as much of it as we can and put it onto one page, so you can use this video to help you with revision. So let's start off with a definition for a field. What do we mean by a field? So a field of force is a region in space within which objects with a particular property will experience a force. Now, first of all, I want to draw your attention to that word region. It's important to use the word region rather than area, because area would imply that it's only 2D, but a field of force acts in the 3D. If we look specifically at a gravitational field is a region of space within which mass will experience a force. Within this video, whenever we're talking about gravitational fields, it'll be written in blue. If we compare that then to an electric field is a region of space within which charge will experience a force. Within this video, anything to do with electric fields will be written in red. We're going to aim to do a lot of the explanations here side by side so that you can see the similarities between both gravitational and electric fields. So now that we have a definition for fields, let's have a closer look at the forces within those fields, and we'll begin with the gravitational fields. So we'll begin by looking at Newton's Law of Gravitation. So Newton's Law of Gravitation tells us that between every 2 point masses there exists an attractive gravitational force which is directly proportional to the product of their masses and inversely proportional to the square of their separation. So let's look at how does that translate to an equation. We're saying that the force that acts between these two masses is directly proportional to the product of their masses. So I'm going to call the masses M1 and M2. Now these masses are measured in kilograms. It is also inversely proportional to the square of their separation, which means if we divide that by their separation, we're going to use the letter R for that. So R is representing the separation between the 2 points, the distance between the 2 points, and that is squared. And that separation is measured in meters. So at the minute we have an expression, but what we really want is an equation. So to change this into an equation, what we're going to do is we're going to get rid of that proportional sign and we're going to replace that with equals some constant multiplied by M1, M2 over R squared. Now it turns out that that constant is the universal gravitational constant, and we use the letter capital G to represent that. Now this has a value of 6.67 by 10 to the minus 11, and that value is given to you on your data sheet, so you don't need to memorise that, but you do need to be able to use it. It's important to understand that when we're talking about the force between masses, this force is always attractive. So just the way a force exists between any 2 point masses in a gravitational field, there also exists a force between point charges in an electric field. And this gives rise to what's called Coulombs Law. So Coulombs Law states that between every 2 point charges there exists an electrical force that is directly proportional to the product of the charges and inversely proportional to the square of their separation. So I'm sure you can see the similarities with the Newton's Law of Gravitation. So very, very similar here. So let's translate that into an equation just like we did with Newton's Law. We have F is proportional to the product of the charges, so we'll call that Q1 and Q2, and inversely proportional to the square of their charges, so we have divided by R squared. And the constant in this case, if we get rid of that proportional sign and replace that with equals a constant, in this case the constant is 1 over 4 pi epsilon naught. So epsilon naught is the permittivity of free space, and this is a value that is given to you on a data sheet, and it has a value of 8.85 by 10 to the minus 12. So again, you just need to be able to use it. You don't need to memorize that number. In fact, we could actually work out what this constant is, and usually we can just shorten this equation to k multiplied by q1 q2 over r squared, and in this case k works out to be 9 by 10 to the power of 9. So that's a simplified version of that equation, but just be mindful that this value k, the 9 by 10 to the power of 9, that value is not given to you on a data sheet. So one important difference between the force between charges compared to the force between masses is that when we're looking at charges, that force can either be attractive or it can be repulsive. So if we have two charges that are the same, for example, two positive charges, well, we know that two positive charges will repel each other. So if Q1 has a positive value and Q2 has a positive value, then overall the value for F will be positive. The same is true if Q1 was negative and Q2 was negative. Well, two negative numbers multiplied together will also result in a positive. So anytime we have charges that are repulsive, the value for F is positive. However, if we have opposite charges, then we will have an attraction between those opposite charges. So if Q1 was positive and Q2 was negative, well, when we multiply that together, that result is a negative. So therefore, if that force is attractive, then the force is negative. Now that we've had a look at the forces, we're now going to look at field strength. So I'm going to go back to the gravitational fields here, and we're going to look at gravitational field strength. So the gravitational field strength is defined as the force that would be produced on a test mass of 1 kilogram at that point. So to put this into an equation, we define the gravitational field strength. We use the symbol G, and that's a lowercase g. And in fact, you've met this before. In the equation, weight is equal to mass times g, the acceleration due to gravity. That's the same value here. So G is equal to the force produced on 1 kilogram of mass. So the force per unit mass, which means we're going to divide it by m. From this equation, that tells us then that our units for G can be written as the Newton per kilogram. Now, since G is equal to F divided by m, and we know that F is equal to capital G, m1, m2 divided by r squared, well, we could also put that into this equation. And when we do, it cancels down to leave us with capital G multiplied by m divided by r squared. So two different equations here that we can use in order to figure out the gravitational field strength. So now we'll have a look at how we'll define the electric field strength. So the electric field strength is defined as the force produced on a positive test charge of 1 coulomb at that point. So we need to think about what would happen if we were to place a positive charge at that particular point. So to put this into an equation, we use capital E to represent the electric field strength, and that is the force produced per coulomb of charge. So we're going to divide that by Q. So Q is representing charge. From that, we can see that our units for electric field strength could be written as the Newton per coulomb. And again, using the equation for the force, for electric force, we could also say that the electric field strength is equal to K multiplied by Q divided by R squared. And just remember there that K was just a shorthand constant that represented 1 over 4 pi epsilon naught. So how might we visualize the strength of these fields on a diagram, or how might they be represented? They are represented by field lines. So field lines tell us two things really about the strength of a field. They tell us the direction that the field is acting in, and they give us an indication of the strength of the field. And that is because the closer together the lines are, then the stronger the field is at that point. So first we're going to look at gravitational fields and how we would show that then on a diagram. So let's say we have a large object of mass. For example, this could represent a planet. Well, the field lines around that are always going to be pointing towards that object, towards that planet. So the direction of those arrows is really important. What we can also see is that around the surface of that planet, the lines are closer together than they are further away from the planet, which would tell us that the gravitational field strength is stronger at the surface of the planet than it is some distance away from that planet. And what we find is actually we have an inverse square relationship, which we'd mentioned already in our definition for the force. And that field strength decreases the further we are from that object, or from a planet, for example. So gravitational field strength here is on the y-axis, and the distance from that is on the x-axis. Now, we're not really too concerned with what's happening in this section here. We're starting from the surface of the planet, and as we move away from the surface of the planet, that value for G decreases. And we would describe this shape of field as a radial field. Now, if we were to look at the gravitational field strength on the surface of a planet, we do say that it is approximately uniform, that it has the same value throughout. So if we were to draw field lines to show that, then those field lines would be equally spaced and they would be parallel to each other. So we would describe this field as uniform. Now, if we consider the field lines around a charge, we need to be a little bit more careful, because we need to take into consideration the fact that we need to figure out where a positive charge would go. So let's say we have a small object here with a positive charge on it. And we placed, at this point, we were to place a small positive test charge. What way would that charge move? Well, if this little point is positive and our charge itself is positive, then they're going to repel. So that means that it's going to move away from the charge. And what we find is that the radial field we have around a charge will look like this, where the field lines are pointing away from that positive charge. However, if we were to consider a negative charge and applying the same process, if we had a point positive charge here, well, that positive charge would actually be attracted towards the negative. And so our field lines would be pointing inwards rather than away. And they are attracted towards that negative charge. So that's one thing to look out for in a question, is to be aware what type of charges are we dealing with and what way are they going to interact with each other. Will they repel each other or will they attract each other? And what effect then will that have on the field lines? It is possible to have a uniform electric field, and that can occur if we set up an electric field between two plates, for example in a capacitor, where one plate has a positive charge and one plate has a negative charge. So again, let's consider what would happen if we were to just pick a point here in the middle and imagine that that is a positive test charge. What direction is that going to move in? Well, that positive charge is going to be attracted towards the negative plate and repelled from the positive plate. So it's going to act down, which means our field lines are acting downwards from the positive to the negative. And again, this is going to be a uniform field, so those lines are going to be equally spaced and parallel to each other. Because remember, if they're closer together at any point, that would indicate that it's stronger at that point. So for a uniform field, those lines need to be equally spaced. So our electric field is going from positive to negative. We could actually work out the strength of this electric field if we had two pieces of information. If we knew what the separation of those plates was, in other words, how far apart they were, we use the symbol D for that, the distance between the plates, and if we knew the potential difference across the plates. And those are linked together by the equation E, the electric field strength, is equal to the potential difference across the plates, so we use V for that, divided by the separation of the plates, and that's the lowercase d. In this equation, the potential difference is measured in volts and that separation is measured in meters. When we have the field set up like this, what we find is that the further away we are from that positive plate, the less the potential difference is. So if we were to actually plot that onto a graph where we have the distance from the positive plate on the x-axis, and we were to plot how the potential difference changes, then we actually find that we end up with a negative straight line. So what we're doing here is we're plotting potential difference there on the y-axis. We are plotting the distance from the positive plate on the x-axis, and we do get a straight line, so that means there's some constant here, and because this is a negative line, we have a negative constant. So actually this constant is the electric field strength, which is why our equation is sometimes written then with a minus in front of it. But usually it gets left out when all we're interested in is the magnitude. But that minus there really is just to indicate that we are moving from a higher potential to a lower potential. So what we can see then is that there are quite a lot of similarities between the gravitational and electrical fields. We use very similar equations to describe the forces. We use similar equations when describing the field strength, and we use that same notation whenever we show the field lines. The one thing we need to look out for is the fact that when we're looking at electric fields, charges can either be positive or negative, which means these forces can either be attractive or repulsive, and we need to bear that in mind when we're drawing our diagrams and when we're putting those values into equations. So now we'll put all these similarities and differences together in the one table. So if we start off looking at the similarities, both electric and gravitational fields follow what's called the inverse square law, which means that the field around a point mass or the field around a point charge will decrease the further you are from that test point. And it is proportional to 1 over r squared. Also, both have an infinite range. So if we have a look at the differences, gravitational fields act on masses, whereas electric fields act on charges. So the property upon which that field will have an effect is different in the gravitational and electric fields. When we look at gravitational fields, they're always attractive, whereas an electric field can either be attractive or repulsive. And finally, gravitational fields are impossible to shield, which means there's no way of blocking out the effect of a gravitational field, whereas with an electric field, it is possible if you have a suitable material. So next we're going to focus on a few more points that are concerned with gravitational fields. And we'll begin by looking at Kepler's third law. Kepler's third law refers to planetary motion. It states that the square of the period of revolution of the planets about the Sun is directly proportional to the cube of their mean distances from it. And we can write this as an expression by writing t squared is directly proportional to r cubed. Or another way of writing that would be to say that t squared is equal to some constant multiplied by r cubed. Now, a common question you could get in an exam would be to show that Kepler's third law is consistent with Newton's law of gravitation. So this next bit, you need to be able to recreate that in an exam. So let's consider the case where we have the Earth in orbit around the Sun, and the Earth is moving around the Sun in a circular path. We know that there needs to be a centripetal force in order to keep an object moving in a circle. And for planetary motion, that centripetal force is provided by gravity. So we know an equation for the gravitational force and we know an equation for the centripetal force. So we're going to put those two things equal to each other. The equation for the gravitational force, which we met at the start of this video, is G, being the universal constant, is equal to m1 times m2 over r squared. But instead of using m1 and m2, I'm going to use the mass of the Sun and the mass of the Earth, all over r squared, where r is the distance between them. That is equal to the centripetal force, and that's the centripetal force that's keeping the Earth in orbit around the Sun, and that equation is mr omega squared. Omega here is the angular velocity, which we met in an earlier topic, and it's given by the equation omega is equal to 2 pi f, which is also the same as 2 pi over t. Now it's this version of the equation that we're going to take and substitute that back in. Now remember that omega was squared, so therefore this expression also needs to be squared, and that's an easy mistake to make when you're writing this out. Next thing we're going to do is we're going to multiply out what we have in the brackets. Now we should see that on both sides of the equation we have me, so those terms will actually cancel out. Now remember that the point of this exercise is we're trying to show that t squared is equal to some constant multiplied by r cubed. So that means we're going to need to gather together all the r terms. So we're going to rearrange to bring r squared over from the left hand side to the right hand side. And next we're going to bring the t squared from the right hand side over to the left. So finally I'm going to bring the g and ms over to the right hand side where it becomes a divide, so that we are left with t squared is equal to, we have r cubed 4 pi squared over g ms. Now I'm going to rearrange that slightly just so that it matches the format that we have at the top, because we wanted to show that t squared was equal to some constant multiplied by r cubed. So we have t squared is equal to 4 pi squared over g ms r cubed. Now if we look more closely at these terms, we have 4, which is just a number, which therefore is a constant. We have pi squared. Pi again is just a number, so it's a constant. We have g, which is our gravitational constant. And then we have ms, which is the mass of the Sun. And in this case, it is a constant. So everything there is indeed a constant. So we have shown that t squared is proportional to r cubed. This equation can be used to estimate the mass of the Sun, which we assume to be constant over its lifetime. We can also apply these equations to satellites. In particular, with geostationary satellites, there are a few facts that you need to know and be able to apply to your calculations. So a geostationary satellite is one which is always above the same point on the Earth. It orbits above the equator. It orbits in the same direction of rotation as the Earth, which means it also goes around anticlockwise. And it has the same orbital period, which means it takes 24 hours for it to make one full rotation. Now, if the time period is fixed to 24 hours, that also means that the radius is also fixed. And therefore, the height above the Earth's surface is also fixed. And that can be determined using the previous equation. So these facts you need to be aware of, and you may need to apply those to questions regarding satellites. When it comes to calculations, you may be asked to determine the force or the field strength at a particular point where you have one or more masses or charges. So let's just have a look at how we would deal with that. We could have 2-point masses, M1 and M2, or 2-point charges, Q1 and Q2, and we could be asked to determine what is the force or the field strength at a particular point. Now that point could be in the middle of the two charges or the two masses, or it could be off to the side. In any event, it doesn't matter because you treat it in the exact same way. What we need to do is we need to consider what is the force or what is the field strength due to each mass or charge separately. So we consider them individually. Once we've determined the force or the field strength individually, then we combine them to determine the resultant. So the direction is going to be important here. Remember that gravitational fields are always attractive, whereas electric fields can be attractive or repulsive. And we always consider what would happen if we were to place a test charge that was positive. We could also consider the special case where there is a point in between the two masses or the two charges where the force or the field strength cancels each other out. And as such, the resultant is zero. And we call such a point a neutral point. So at a neutral point, the resultant gravitational field or the electric field strength is zero, which means that if we consider the gravitational fields, it means that at this particular point, mass 1 is pulling at it with the same force per kilogram as mass 2. If we apply that same logic then to charges, that means that charge 1 is either attracting it with the same force per coulomb of charge as Q2, or it is repelling it with the same force per charge as charge 2. Therefore, we're only going to have a neutral point between two charges if both of those charges have the same type of charge. In other words, they're both positive or they're both negative. In an exam, you could be asked to find the location of this neutral point and how far it is away from one of the masses or one of the charges. So to do that, we would make use of the fact that the resultant field strength at that point will be zero. Now it's important when you're faced with a question like this that you label any information that you have onto the diagram. So let's say these two masses are separated by a distance r. We want to find out how far this neutral point is from M1. So that means this is the distance we are trying to find out. So we would label that unknown distance as x usually. Now if we know the separation of the two masses, then we could come up with an expression to tell us how far away that neutral point is from the second mass. That would be given as r minus x. And that's going to be useful when it comes to putting values into the equation. So at a neutral point, the resultant gravitational field strength is going to be 0, which means that the gravitational field strength because of M1 is equal to the gravitational field strength because of M2. They're going to be equal in magnitude, but acting in the opposite directions, so that overall the resultant is 0. Now if we look at the other equation that we have then for the field strength, that would allow us to write gm1 divided by x squared, because x is the distance from this neutral point to M1, would be equal to gm2 divided by r minus x all squared. And that's because r minus x is the distance between the neutral point and M2. Once we have that expression, then it's just a matter of plugging the numbers in and working out x. Now once we have those values, we can plug those into the equation to get the answer and work out x. Now these questions where you're asked to work out the neutral point or to find the force or field strength at a particular point, they can be extremely tricky. So really what you should try and do is get a lot of practice at these sort of questions. You could also have a look at some of the videos that work through these examples. So that's it. That's an overview of gravitational and electric fields, and I hope you find some of that useful. What you should do next is complete lots of practice questions to make sure that you really understood this topic.